Everybody find it? So lesson 3 is called position time graph. And remember this thing from a while ago when we used this for like distance and displacement? Well, now we're going to look at like graphs for it. And there's two types of graphs we see throughout the year, especially when we do labs. Our first lab could come as early as next week. We gotta get through the graphing stuff, so when we get graphs from sensors like this is a motion sensor. And we'll do some labs where we have maybe us walk in front of it and get graphs from it, or have carts on this tracks over here that go in front of it. And we need to be able to interpret what those graphs tell us by their shapes. So to be able to do that when that time comes, that's why we're doing this lesson right now. There's VT graphs as well we'll probably get to late this week or next week. So anyways, I'm going to use the simulation. But basically imagine that this guy's walking in front of something like a motion sensor. Alright? Basically, to give you a quick rundown of how one of these things works, it's really similar to a radar gun that we talked about a little while ago. It puts out invisible waves, radio waves that we can't see, that bounces off an object moving in front of it. And it happens so quickly because the waves move at like 300 million meters per second that it comes right back to it. And the time it takes to hit something and come back, it knows that. It basically records that. And if you're moving in front of it, the time is greater or smaller depending on if you're closer or further. And it's able to like immediately graph that motion. So basically we're going to pretend that's things going on with this guy. Pretend there's a motion on the simulated guy up on the screen. Alright, so we're actually first not going to move him. We're going to first look at a position time graph that does not have any motion to see how simple it is. So I'm just going to let it play for a couple seconds. Let it play. And nothing real fancy happens, nor should it, because he's not moving, right? So if this guy was standing in front of a motion sensor on this axis, I'll let it go to about 6 seconds. Stop. That just stayed a flat line, didn't it? You see that? So basically that tells us something. On one of these graphs, anytime you have a flat line, that means you are stopped, or the object is stopped. Right? This one happened to be flat at 0 because look where he is. On this number line, he's at what we would call the origin, the 0 meter mark, right? So I'm going to move him over. I know the graph started again, but I'm going to move him here. He's about at 4 now, right? I'm going to hit play, and now the line's still flat, isn't it? Right? He's just staying steady at 4 meters about now, right? Instead of staying steady at 0. So flat lines will be flat along the axis that matches where on position-wise. And that's the y-axis, the position axis. There he is. This axis is a time axis. As time goes on, this is 2, 4, 6, 8, 10 seconds, and so on. When we name these graphs, we always call them whatever's on the y-axis versus whatever's on the x-axis. So this is position on this one, so it's a position versus time graph. That's simply how we title it or call it or refer to it. All right, I'm going to reset it now, and we'll look at some other motion. I'm going to reset it. We'll look at those ones later. All right, he's still going to start at the origin, and I reset it. Now I'm going to try to make this guy, and I can't do it perfect because it's how steady my hand is. But I'll get as close as possible. I'm going to make this guy move as close to a constant velocity as possible. Just remember something from the past. If we move at a constant velocity, then what's my acceleration? Yeah, 0, good. Because acceleration is speeding up or slowing down, right? Or changing direction, but we're going to focus on the speeding up, slowing down thing. If I don't speed up or slow down, there's 0 acceleration. So constant velocity means 0 acceleration. I'm going to try to move this guy with my cursor, with my mouse, and move him in the positive direction. See where the numbers get higher? And if I don't do it great, I might reset it and try again. But we're going to look at the graph after I do that. I'm going to hit play. It's going to stay flat for a little while until I move him, because he stops still, right? Then I'm going to start moving him. Real steady, Ed. Pretty steady, right? Pretty good. Not perfect, got a little bumpy in there, right? But pretty close to a straight line, isn't it? So here's the deal. If I could do it perfect, which I can't, if I could make him move perfectly steady, that would be a perfectly straight line from that point to that point, from when he stopped to when he stopped again, okay? So this tells us something. If something's moving at a constant velocity, our lines are straight. They're just not flat anymore, okay? So there's a fancy word for straight lines in math that I'm sure you all heard of. Starts with the L. Anybody remember it? Linear, very good. Linear means straight. Doesn't have to mean flat. Flat lines can be straight, but this line's linear as well, right? This slanted line, this diagonal line. So something real important to start today. In general, if on a position time graph you have a linear graph, that means that thing that made that graph, that straight line portion of it, was moving at a constant velocity. Even if that constant velocity was 0, wasn't it? Isn't this flat line linear? Right? So that just means I constantly stayed at 0, right? Here I constantly stayed not moving. I stayed at 0 meters per second. The slope of the line, use some math pens here. The slopes of these lines, we all kind of remember how to find slope? If not, we'll review that either today or tomorrow when we get to it. But the slopes of these lines give the velocity. It directly tells me how my position's changing. But if I find the slopes of these, it represents velocity. So steady slopes means steady constant velocity. Make sense? I can do it backwards too. I can make a line. I'm going to hit play again here. I'm going to move them steady in the other direction. You probably predict what's going to happen. That's a straight line again, right? And now it's sloping which way? Obviously, instead of up, down. Or in other words, that would be called a negative slope, isn't it? All right, so, again, since you've definitely all learned somewhere in the past about slope. With linear straight lines, there's 4 different types of slopes in math that could happen. But in reality, like a real situation like this, only 3 out of the 4 could really truly happen. We'll get to why in a second. So, we have 3 out of the 4, though. We have a slope of 0. That's a flat line. And be careful. No slope and 0 slope do not mean the same thing. A flat horizontal line, like here, right here, and right here. There's 3 places on this graph in the segments I made. Here, here, and here that have all 0 slope. This one, let's just be general. We don't have to find it exactly right now. This has a positive slope because it looks like it's going uphill, right? And this has a negative slope because it looks like it's going downhill. Since they're all linear, they're all constant velocities, though. There's one other type of linear line, though, you discussed in math way back when. And that was vertical lines. Let me ask you this. I can't make one because it's impossible, so let's pretend. What would it mean if I had a position time graph of a guy that was completely vertical? Let's say like along this vertical line right here of the grid. What would that be? Why would that be impossible for something to move like that? Why couldn't I do that? Why couldn't any object do that? Yes. Okay, I see where you're going because it's up and down, right? I see where you're going, but not correct. Okay, let me do something to lead you in the right direction. I'm going to hit play again. I'm going to go positive again. Still going to try to go steady, but I'm going to try to go steady a little faster, okay? And we're going to compare something. Pretty steady. Still a little bumpy, but not bad. All right, let's compare 2 pieces of the graph. This was positive as well, right? Positive slope, and so is this one. But notice when he went faster, what happened to the steepness? It went up. The slope got greater, didn't it? So if we have a positive slope here and a positive slope here, the steeper positive slope is the faster one, isn't it? Now, what if I went a little faster? It would get steeper, right? Did I ever go so fast that it's straight up and down? No, you're right, no, but why? Let's say at the 16-second mark right here, let's say it's straight up and down. That's a problem because remember what's on this axis, the position, right? That would be trying to say, if it really were straight up and down, that the 16-second mark is an instant in time, right? It's a moment, right? That gets passed through. Could something like a person or any object be at 0 meters, 5 meters, and 10 meters? Look at this axis. All at the same time? No, you can't be in different places at the same time, can you? That's what a vertical line would represent. That's why it doesn't even have a numerical number. It's either called undefined or no slope. Both mean the same thing. But that's way different than 0 slope because 0 is a number, isn't it? 0 slope on one of these really means your velocity is just 0. The slope, exact value for slope represents your velocity, okay? That's possible, having zero velocity, right? It's not possible being many places at once. And that's what that would be trying to say. So that's why in math you call it undefined, can't happen, right? And positive velocities and negative velocities based on these slopes here, here, and here can happen, right? So to sum it all up, in the end, linear graphs, linear means not having curves, straight lines, all have constant velocities. And this one can't happen because you can't be in many places at once. All right, let me reset. This one's a little trickier for me to make. So I'll might take a couple times. I'm going to not move them steady. I'm actually going to do kind of some crazy motion first. We won't actually analyze motion this crazy, but just to prove a point, I'm just going to whip them all around, basically. So I'm going to hit play, and when I hit play, like a motion sensor starts, okay? It tracks his motion. You stop. Now I'm going to do like crazy stuff, like turn around, all kind of turn around. Now parts of the graphs are still linear, aren't they? Like if we took a chunk from here to here, that's a straight line from there to there, it looks like, right? And that's a straight line from there to there. And we got a bunch of little segments, pieces that are straight lines, right? So any pieces, time intervals that still have pieces that are straight lines, he was still going constant velocity then. But we have a lot of curves now, don't we? And in particular, these curves are called parabolas. You might remember that from math. When we see curves on a graph, what that represents on a position time graph, like this, that represents some kind of acceleration. And one more time, what are the ways to accelerate we learned in the past? Right, speed up, slow down, and changing direction, right? Now the changing direction one really refers to going around a turn, but we're not there yet, so we're only going to care about the speeding up and slowing down type. So anywhere we see a curve, it means we are either speeding up or slowing down. We're going to analyze exactly how much on some graphs on the study guide to show you what that means. But so I made a kind of crazy one here. Let me reset it and just try to make a somewhat nicer curve, at least a partial curve. All right, so everybody see right in here is a pretty good curve? I know it goes steady then, that's okay. But right in here, for maybe a second, I get a good curve, right? So he started from rest. And to get him to move, he had to speed up, right? So look at this curve right here. And notice, doesn't the curve get steeper as time goes on? If the curve gets steeper as time goes on, then you're speeding up. So you could have a curve that goes this way and gets steeper. So I could have a curve that moves downward and gets steeper, can't I? I could have it go like this and get steeper downward. That would just mean the other way. Let me move them, speed them up in the opposite direction. Here we go, a little bit, not much of one, but a little curve right here. I sped them up going this way. So there's two ways to represent speeding up. Either a curve that sweeps up like the first one, or a curve that sweeps down and gets steeper. Didn't it get steeper as it went down? Those both represent speeding up curves. Those are the only two types we're going to have. This is called speeding up in the positive direction, that first one. This is speeding up in the negative direction. Now, what I also did, there's a little curve right here, isn't there? This curve right here, earlier, did it get steeper or not? Look through the curve as time goes on, from like there to there while I'm moving my cursor. Did it get steeper or did it flatten off? Look what happened. Is it getting steeper or flattening off? Flattening off. When a curve gets less steep or gets closer to flat, that means you're slowing down. All right? That's how the other form of acceleration is represented. It happened down here too, just in the negative direction. Down here, we had a little curve. I know it's small. But we have a little curve that flattens off. It flattened off completely. That means it eventually came to a stop. So steeper curves that get steeper as time goes on in either direction represent speeding up. Curves that flatten off represent slowing down. So with all that stuff in mind, you're eventually, it's still a little ways off till we get completely through the graphing unit. That's not the end of it. We're going to do a real lab where you will be the people moving in front of this and making some of these yourselves. But first, you got to understand this going into the lab, so you're not like clueless, like reading your graphs and what it means to answer all the questions in the lab. So hopefully, at some point next week, maybe by the mid or end of it, everything goes well, you guys will be doing that lab together. All right, so now I'm gonna flip over to the study guide on my squid, and we're gonna start it. Now there's a review part here that's kind of important for a later part in these graphs. Old stuff in physics always comes back at some point. We always almost have to remember something from earlier because things just build on each other in this course, okay? So we answered a question like this in the past, and it's going to be important for some of the graphs later. So let's do this review real quick. Just fill this out together with me. Once we finish this, we probably won't finish this today, but once we finish this, I want you to submit it even after we do it together so you get a few points for having it complete, okay? So moving in the positive direction and speeding up, it says categorize the following motions of either positive or negative acceleration. Remember we said that the only way to speed up is if the sign of your velocity, or which way you're moving in the first place, in other words, if that sign and your acceleration sign are the same. We did a study guide where that happened. There was a question on a quiz on something like this. So if we're moving positive and we get faster, that means speed up, right? That means your acceleration has to have the same sign of the direction you're moving in. So we just need to put signs on these lines. Positive. Oops, I'm on my eraser still. There you go. So we put a plus there. Because plus means speed is one way to mean speed up. All right? Moving positive, accelerating positive, plus is one way to speed up. But I'm actually going to answer these out of order because of similarity. Something like. Let's jump down to C. I could also speed up in the negative direction. If I'm moving in the negative direction, let's say this way now. If I want to speed up, I got to accelerate that direction. So negative accelerations can mean speeding up. This all goes back to a day, like a week or so ago, maybe not even that long. If you remember me saying, us figuring out that a negative acceleration doesn't have to mean slowing down, does it? If you're moving negative and accelerate negative, then that also represents speeding up. And then if you have opposite signs, that's when it's slowing down. So if I'm moving positive or have a positive velocity and I slow down, then my acceleration has to be opposite, negative. And similar in part D, this is a slowing down or getting slower one. If I'm moving negative and slowing down, my acceleration has to be opposite of the way I'm moving. So if I was moving negative, this acceleration is positive. You guys kind of remember all that? You'll see why we reviewed that at some point either today or early tomorrow. All right, so now let's move into after we talked about the moving man simulation. Some of these graphs are very general, so like multiple answers could be correct for some of them. But let's be all on the same page and I'll put the same answers together, okay? And by the way, after you submit this, whenever we get it done, there's going to be some kind of assessment on this. It's either going to be a form of an open note quiz, okay, which you're going to be allowed using these, so make sure you fill them out correctly. Any of these graphing study guides, I'm going to let you have opened up, all right? If we have that subscription for Physics Classroom that I said we will real soon, instead of a quiz, it might be a concept builder graded for code action. But that's only if we get our login soon, before we're done with this unit, which hopefully happens. All right, so anyways, main point, make sure you save these when you're done as well, so you could use them and pull them up as needed. All right, so let's see what we remember from the moving man thing. We got to draw two lines in each box described by A and B, and we'll label them. We should probably color them two different colors so it looks nice, okay? So, I don't care what colors you use, I'll use the same thing. So what did we, remaining at rest, or in other words, staying stopped. What kind of line represented staying stopped? Go ahead, go. Be a little more specific. You're kind of right. The straight lines could go in a lot of directions, can't they? So be more specific. It is straight, but more specifically how? I think you mean the right thing, but still more specific. Flat, right? Straight flat line, or in other words, a linear flat line. Anywhere, really. Doesn't matter where. If it's flat, that means it's at rest, okay? Now the next part B in this one is a very general statement. Just about anything that is not this is moving. Let me get this full screen so it's a little better. There we go. So really any line that is not linear, but it still can't be straight up and down because we explained how that one's impossible. Any graph you draw that is not flat and not straight up and down is represented in motion. But let's make a simple one. That would mean the thing's moving, right? So would even a curve, because it didn't say how moving. It didn't say constant velocity and it didn't say acceleration, just some type of motion. That would be representative of some type of motion. All right, next. Two at once. We couldn't do this with the simulation because there was only one guy, right? Let's say we have two people. And let's say they're both moving constant, so they're going to be linear, okay? But one person, person A, is moving slower than person B. How might you notice that from graphs? Like you weren't there, you didn't see it, okay? There were two people in the hallway. One of them moved faster than the other. How would their graphs different? Think of slope. We kind of mentioned this when we were going over the moving man one, but we couldn't do two at once. What would the slope of a faster person's line look like as compared to the slope of the slower person's line? Yes. More vertical, steeper, right? Exactly. So all we got to do for a slower person, we got to draw it closer to flat. Not flat because flat would be stopped. But if flat is stopped, just a little bit above flat would be moving slow, wouldn't it? So let's have the slow person just still slope, but only a little bit compared to the second person, person B. Because the slopes of these lines represent the velocity. A steeper slope means a faster moving object. Make sense? Okay. Moving on to the next one. Third one on the top row. Alright. This one's pretty general as well. Moving in the positive direction. So that would be anything. The positive direction, remember this axis right here is a position. The y-axis is position. Positive position, I know there's not actual numbers on here. But positive positions grow this way, right? Negative positions would be down here, wouldn't it? Right, I know we don't have that quadrant showing here, but these would be negative positions. Those are possible, because if I'm the moving man simulation, if right here's the origin, 0, that way's positive and that way's negative, right? So I could have a fourth quadrant, they just means anyway. But if I move in the positive direction, that means I move towards numbers getting more positive. Where do numbers get more positive? As I sweep upward, right? So any graph that moves upward, so let's say something like this, would satisfy that. That's an example of moving in the positive direction. Therefore, if we know that, moving in the negative direction would be something like this, right? Let me just clarify something that's sometimes a misconception on this. Just because you're moving in the negative direction doesn't have to mean that you're at a negative position. Let me do an example of that. Here's 0, right? The origin. That's the negative direction, right? I could just be simply, this graph we drew right here for B on the third one, I could be moving towards the negative and not be in the negatives, right? And I'm still moving in the negative direction. Does that make sense? I don't have to be actually at negative position value to be moving towards the negative direction, right? Because I could cross the origin and now I'm in the negatives, right? So the whole time I'm moving towards more negative, more negative, more negative. So that's what that represents. All right, questions so far? Again, you don't really have to, you just have to understand this. You don't have to necessarily memorize it. I'm always going to let you have these in front of you for anything that might be graded on this stuff. All right, now we're going to get into some other things. In a moment here, there's going to be curves involved, but not quite yet for A. Moving at constant speed. Remember, constant and linear go together. So any linear graph would satisfy line A on this one. Even a flat one. Being at rest is just constantly being at 0, right? At 0 velocity. So you could draw a flat one, but any linear line means constant speed. Okay? Any linear line means constant speed. What did we say in general? There's different variations of it, but this just says accelerating. It doesn't say speed up or slow down, so it's being general here. What does it in general? We said when acceleration happens, there's going to be some kind of what? If it's not linear, that means there's a what? Curve, some kind of curve. It doesn't tell me what kind because we don't know speed it up and down, it's slowing down, so let's just draw some kind of curve. Let's do something like that. That's a curve, right? That would represent on these graphs there's some kind of acceleration going on. What kind? Well, it depends, so we'll look closer at these ones. Now we're getting way more specific. It tells me speeding up, slowing down, and the direction we're going in. All right, so let's start just a little bit at a time here. Just pay attention. It's really not that bad. Let's just make sense of it. Moving in the positive direction. Remember, which way is the positive direction? Upward, right? And if we're speeding up, remember what I said on that simulation, the line's got to get steeper, right? So I need to go upward and get steeper as I go upward. So line A, to do that, would have to look like that. It has to look pretty much exactly like that. You can see it sweeping upward. That means I'm going positive. You can see the lines getting steeper. Remember we said the steepness represents going faster. The steepness keeps increasing, doesn't it? Right here on the curve is less steep than right here and right here. It gets steeper as it goes. That means we're speeding up. Makes sense, right? Now, how would we draw one? Let me ask you guys. How would we draw one that's still moving in the positive direction? It represents slowing down in the positive direction. It still has to sweep upward. But how would we have to vary that? Yeah. Right, or in other words, not get steeper, right? So the only way to do that would be to kind of almost flip this curve around. It still needs to go upward like this to move in the positive direction, but I would draw it flattening off like that. It doesn't even have to get completely flat, but I would draw it flattening off. That would be what line B goes. So we can see moving positive, right? Sweeping upward. But because, and keep remembering, flat means you're stopped. So if you slow down too much, you might come to a stop, right? And that's what this is showing, right? I'm getting flatter, less steep, flattening off. So that's why it represents slowing down. Now the next one, and this will be the last one we do on here today, because I have some other stuff I'm going to talk about before we do the remainder of this. We'll finish tomorrow. We still have speeding up and slowing down, but what direction are we moving in while we're doing it this time? The negative direction. So you got to think about that. Now our graphs have to start up and sweep downward to move in the negative direction, right? And to speed up, we still got to get steeper. So still, though, so the only way for that to happen, to move in the negative direction, is to sweep down like that. It's moving towards the negative direction because it's going down, right? And we can see it's dropping quick, right? It's not flattening off, is it? It's getting steeper and steeper and steeper. So that just means speeding up in the negative direction, which is possible, right? And then that's describes line A. And then the flip side of that would be going downward and flattening off, which would mean going like that. Slowing down, getting flatter, 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 less steep. Any questions on any of those? Really, the next 4 boxes, which we'll continue on tomorrow, are really the same 4 that we have here, 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 and here, but they ask it in a different way. And then we have some flip questions. Instead of making the graphs, we're giving them and have to explain them. Let's go in the reverse of this. And then we get a little bit of math. We'll actually find real slopes at some point tomorrow, all right, at the final part of this one. But if you understand what we did so far, you got a pretty good grasp on this stuff, all right? But none of these gave us or asked us to do anything where there was a full parabola. These are just partial parabolas, which happens most of the time. But full parabolas could happen. So just pay attention on this. You don't have to write this down, okay? We'll end here today. We got, what, about less than 10 minutes. So there might be a couple minutes left, but this will be a good place to stop. I'm just going to make my own graph. I'm going to draw an axis. I'll include a 4th quadrant, although I guess I don't have to. But this, again, like all these other ones, position on this graph, time on this graph. Position versus time graphs is what we call these. But what if we did give you a graph that had like a full parabola like this, not just a partial one? If I just gave you the graph and asked you to explain to me, give me as much detail as possible about what an object, how it would have to move on a linear line, this way or that, to create a graph like that. what's happening in this one, since it's a full parabola to the object, since the other ones were only partial ones, right? Well, it might help to break it up. First of all, it's a curve the whole time, isn't it? So we know if it's a curve the whole time, from whatever the time is, I don't care, but from time t equals 0 to whatever time is over here, we know that it's curving. Curvings mean acceleration, right? But the whole time this guy's accelerating. He's definitely not going steady at all, is he? No straight lines there at all. Let's break it up into halves, because we saw partial parabolas. So let's just take, does anybody remember from any math class what the peak or belly of a parabola is called? It starts with a V. And vertex, okay? That's like the turning point of the parabola, which will be right around, I'll put a little dot there. About right there is the vertex, right? So let's look at that first half up to that vertex. Look how this curve goes. What direction are we going in as we approach the vertex, Cal? We're going positive, right? We're moving upward. But is the line getting steeper? No, it's flattening off, isn't it? So based on what we just learned, if the line is flattening off, I'm not getting faster in the positive direction, I'm getting slower. But then a vertex happens, a full parabola, and I keep going, don't I? If I slow down so much, eventually I got to come to a stop. Doesn't the vertex, at least for a moment, look flat? Flat means stop, right? But stop doesn't last long, does it? So that must mean this guy turned around, didn't he? So something like this. If that was the positive direction, this would be somebody that was slowing down in the positive direction. And then, not only did he stop, but immediately after stopping, he turned around and got faster and faster and faster. Because I turned around because now I'm going downward, right? On the graph. On this kind of graph, that means turning around. And as time goes on, it's getting steeper downward, isn't it? Not flattening off, so faster. So basically, this represents turning around. You're going slower here. I don't have to write this down, I'll put it down. Slow here, stop for just a moment, and then we're speeding up here. So the main thing is a full parabola represents you turned around on one of these graphs. It could happen one other way. We'll be more brief on this one. You might remember in math, the parabolas could open two ways. This one opened down, didn't it? They could also open upward. This one just would mean we're going negative slowing down first, because it's flattening off, stopping, and then going faster in the positive direction. Just the opposite of that. Same idea, just different directions. Remember that parabolas cannot, I know this is going to get messy, but right? Parabolas can't do that. We'd run into the same problem. Because if we remember the vertical line test, does that ring a bell in math? If it doesn't, it's just the same idea as we said before. We can't have parses of a graph that are on the same time, right? Because those two dots I made, that person can't be there and there at the same exact time, can they? So you'll never see, it's impossible to make a sideways parabola. They either open up or open down, and that's it. Otherwise, they would represent it sometimes being at the same place at the same time, which we already said can't happen. All right, so that's basically the gist of all this. We will answer more questions on the study guide, just asking the same stuff in different ways. Once this